let's welcome the next speaker. We had a smooth transition from Mark because he mentioned that one of the angles he looked at was inter-satellite links that can also be a source of vulnerabilities, and this is exactly the focus of the talk of Gregory Falco. Gregory, similarly to Harrison, is also a name that comes up very high up on the Google links. If you Google cybersecurity and space, he published a number of articles, quite many of them actually, touching various topics around cybersecurity for space. He's been working at prestigious labs at the MIT. I think now he's working at the Johns Hopkins lab. He will tell us a bit more what he's doing these days. So it's a great pleasure to welcome Gregory. I don't know if he can already hear us. Gregory, are you online? Can you hear us?
Yeah, I can hear you just fine. Can you hear me okay?
Yes, welcome, Gregory.
Awesome.
Super
Yeah.
happy to have you here. Did I miss anything in your resume? Maybe I also mentioned I congratulated Giovanni because he was listed in the under 30 Forbes list in Italy, and I know you were also on that list recently. Just to add that line to your resume.
I try and forget about that one, but yeah. No. Thanks. No, that's a great intro. I appreciate it.
Anyway, the floor is yours, Greg, and we'll talk after for the Q&A.
That sounds great. Well, thanks again for having me, guys. This is an amazing opportunity for me to speak to the European community about some of the space security challenges that are out there. And if I can just say that this is a pretty exciting time, I think, for Europe. Previously, I would say that the US and Russia kind of have dominated some of the space conversations out there, but given the advent of smallsat, CubeSat, picosats, and increasing launch capacities, there's a huge amount of interest in furthering space activity across continental Europe. Like, for example, this morning I was on the phone with the Swedish Space Corporation, and they're preparing for a massive uptick in services. And of course, because of this, it's a good time to be planning. Good time to be planning for security. So today I'm going to be speaking to you a little bit about a problem that we don't have today, but a problem that's coming very soon. And so kind of keep that in mind. This is a bit theoretical, but hopefully there's enough nuggets in there to keep everyone interested. And so the title of the talk is Unpacking Sidestream Satellite-to-Satellite Communication Security Challenges. So just, Matthew did a great job of giving me a intro, so I don't have to spend much time on this, but wanted to give you some context for where I'm coming from. I have all these fancy academic credentials, that's great, but more importantly, I've lived in the real world as well. And so I spent a number of years at Accenture, which is a major management consulting company, where I founded and led their smart cities business. And what this was really about was taking traditional critical infrastructure assets and bringing them online. So how do we IoT enable, sensor enable, actuator enable, and internet enable all of these things that we rely on for our society to function? And this was a really interesting problem to deal with because I guess this was early 2000s, and we were still kind of grappling with traditional security issues with IT server infrastructure. But now we're talking about taking industrial control systems and bringing those onto the internet. And this kind of created a bit of a mess. And so I actually bailed after we realized how much of a mess this was and went to go do my PhD to kind of figure out some of the security challenges with these control systems. And in the course of doing my doctorate work, I started a company that was trying to actually advance embedded system security when it came to these challenges for critical infrastructure. But quickly realized after we had some clients and we had some patents and stuff, that there's actually a huge market problem when it comes to evaluating the security of these cyber physical systems, these control systems. And a lot of it is mired down in legacy infrastructure. And so what was really appealing to me was when NASA's Jet Propulsion Laboratory offered to fund part of my dissertation work to kind of pivot towards that space industry, which does use all these control systems, and they have very complex cyber physical systems that are really exciting and interesting. But they also have the unique opportunity of kind of being not in an entirely greenfield environment, but we're still building here, and there's still a lot to do and a lot of thinking to be done, and that kind of enables a more security from the ground up kind of approach for this stuff. And so I've gotten a chance to work with a whole number of organizations on space system work, and my current lab that I'll be starting as an assistant professor at Johns Hopkins in the Civil and Systems Engineering Department, but I have a joint appointment with the Applied Physics Lab. And the Applied Physics Lab, if you haven't heard of it, it's one of these hidden giants in the US that is a trusted agent to the US government in a whole bunch of different agencies and in military capacities. And so that means if there's a defense contractor, if government needs something done by a defense contractor and they don't really want to farm it out to the traditional suspects, they come to Johns Hopkins Applied Physics Lab for help and figuring these things out. So they do a lot of spacecraft assembly and spacecraft security work for the military. And so in addition to my teaching duties and my research at Johns Hopkins, I also get to participate in that. And I also have a lab at Johns Hopkins called the Autonomy OWL, where we design and break space systems, usually autonomous space systems, but any space systems will do. And so some of the talk that I'm going to be sharing with you today comes out of a lot of the lessons learned and some of the research that we're doing currently in my lab. And just for more context, and I'll wrap up there from a contextual standpoint, but what's kind of exciting about living in both of these worlds of like academia and living in industry as well is that you get to have some great translation opportunities of taking your crazy ideas and bringing them to fruition and to practice. And so like one of my most exciting moments was this past fall, where it seemed that there was parts of some of my research that I had published when I was at Harvard that was kind of copy pasted into the new US Space Policy Directive 5 on space cybersecurity. And so it was just a really exciting opportunity to see people are actually using this stuff that's, these pie in the sky academics are actually working on. It's real, and we're getting use out of this broad community. So I'm excited to share some of the increasing findings that we're having, because hopefully it'll make it into the real world, into all of your companies and into practice. So today we have some very complex missions that are out there, space missions that are out there. And they rely generally on a space segment, so maybe a space vehicle, a satellite, whatever, then communicates back to a ground station, this ground segment with operational support via a link, right, via some kind of communication protocol. And by no means is this simple. This is already a complex challenge to deal with the security of all of these three different pieces, because each of them have security concerns, which we've seen across a whole variety of incidents. And actually, one of my students is in the process of kind of compiling an incident catalog that the community will be able to use in the future. So stay tuned for that. But this is a problem. This is problem enough. However, we're getting to a world where we are actually adding more challenges to this, more surface area of attack. And that surface area is coming in the form of, well, not only are we going to have one space asset that we're talking to from the ground segment and the link segment, but we're going to have a whole bunch, the whole constellation of satellites that aren't just communicating back to the ground station, but they're communicating with each other. And what this harkens back to for me is the era of machine-to-machine communications in the smart city critical infrastructure realm, where we said, oh, well, this is not a big deal because we've always had server-to-server communication. We kind of generally know how to do security for these systems. And so how do we actually, now we can just do it at scale. We'll just put a whole bunch of systems in, and then we'll have those communicate back to the central server infrastructure. But we quickly learned, here on Earth, that that's pretty complicated, and it puts a huge amount of load on central server infrastructure. So it really requires a distributed communication mechanism for the assets that are out in the field. So you can make the same parallel in terms of what's going to be coming from the space world, where we have a whole bunch of these different space vehicles that are going to be not only communicating back to ground segments, but they're going to be communicating with each other. And they'll be also sharing information in ways that we don't currently anticipate. So we have to future-proof some of that communication between these devices. Now, with any device, when there's communications involved or any kind of connectivity involved, or even when there's not connectivity involved, there are security considerations. And because of the increased amount of capacity of these birds that were thrown into the sky, we need to kind of consider that increased surface area that will be part of those space segments. And so this talk is really about thinking a little bit more about the challenges that we're going to be experiencing with this machine-to-machine in the sky communication mechanisms. And to contextualize this a bit, this is not an entirely theoretical problem. At least in the U.S., there was an initiative a couple of years ago, and it's ongoing, called Global Lightning. It's funded by the Air Force Research Labs, where basically they gave, I think at the time, maybe it's even more now, $28 million to Starlink, SpaceX's subsidiary, to launch a whole bunch of satellites into LEO to engage with communication infrastructure in space. And then you also have some of that money that went to the Iridium constellation, which is much older than Starlink, and they're obviously updating their systems and sending a whole bunch of more satellites into orbit. But the whole interesting part here is that part of the core requirements of this Global Lightning project was we need to have a bunch of satellites up there that can communicate with each other, not only one back down here on the ground. So automatically now we have to think, okay, this is not a theoretical problem anymore. We already have stuff up there that's communicating with each other. However, for the most part, these systems that are communicating with each other right now are all made by the same vendor. They're all made by the same they're all engaged by the same operator, and there's not a lot of that integration. And the use of this infrastructure is pretty minimal right now, especially for critical function. So it's a cool proof of concept. We have some interesting insights into how satellite constellations are working when it comes to inter-agent communication, but we don't really have good insight into how something that is a Starlink satellite in LEO can communicate with an Iridium satellite. That doesn't exist yet. And so these are things that we're starting to have to get our head wrapped around, especially from that security standpoint. And this is becoming even more of a challenge as we have organizations of all types throwing more satellites into LEO. For example, the Blackjack program by DARPA is sending up a whole bunch of satellites in the tens. I think they're planning to have hundreds at some point to be able to facilitate this communication infrastructure between satellite to satellite to make things a bit easier to enable that communication, because actually space communication is pretty hard for a whole number of reasons. Just from a not even security standpoint, but just a general challenges standpoint. And the way that we're trying to, and the reason why is because we're often looking at it from an optical communication standpoint. So basically, satellites are sending lasers at each other, trying to communicate. Lasers are cool, and they are great at communication if you don't have any interference, if you know where you're sending the laser. But guess what? We don't have perfect information. And this Nick Bucci at General Atomics, I pulled this quote from the internet, said it really well. He said, getting a laser beam on a spacecraft to point to a laser receiver on another spacecraft accurately with enough power at levels and right waveforms, this is not an easy thing. It's absolutely not easy to engage lasers for communication for space systems. But we're trying to do this anyway. And it's part of, again, another major DARPA program coming out is to facilitate some of this communication infrastructure. And they think they have some good proof of concepts right now, but it's not happening at scale. And I can tell you that there's probably not a whole bunch of security considerations that are going into that first design necessarily, because we just have to see if it's possible. But we need to start thinking about how we deal with the security of these optical links. And there obviously are a whole bunch of threats in space. So often this conference is about cyber threats, but we have cyber threats in terms of we have this picture of an alien, but it's really just cyber aliens, right? We have a whole bunch of adversaries who are interested in taking down our satellites or hindering our satellites infrastructure. We have natural hazards that will also kind of challenge the optical links from satellite to satellite communication mechanisms. We still we don't always fully control bit flipping. This is still a problem. And so got to think about some of these things. And we also have bugs. Bugs are everywhere, human error in the design of this stuff. And so we end up with these challenges as well. And there are a number of problems when it comes to these side-stream communications challenges, is the way I'm characterizing it. And these are known challenges for these optical links. There's the idea of, you have to detect and track the receivers for the satellite-to-satellite link. And we don't really have perfect orbital trajectories on everything. We don't have a perfect way of identifying a far out tiny little receiver that's on a satellite. That doesn't exist today. So again, these are just operational, like engineering problems that we have that are not security related, but security compounds this challenge. We have processing power issues. This is getting a little bit less of a concern for some of the more expensive satellites, where we have satellites like SmartSat, which was released by Lockheed Martin, where you have this containerization virtualized server in the satellite. But most of our satellites don't have that, and so the processing power of enabling the optical communications is a problem. We are ending up with distortion, and distortion of the laser can be because of interference from other satellites. It can be from space junk. It can be meteorites, things like that. It's again part of just the optical challenge. And we also have storage capacity as a consistent issue. Most of our satellites don't have a huge data infrastructure behind it that can store a whole bunch of data, and so the processing of that data is also latent, where it requires even more storage capacity. And then my thing in my head is disrupting this slide a little bit, but system integration. We haven't even begun thinking about that yet as a problem for these satellites that are communicating in orbit. And one of the areas where it's particularly challenging and concerning when it comes to security is that you have statements being made by companies like Starlink saying, oh, well, we have this autonomous functionality to avoid collisions with other satellites. And so that's obviously one of the core use cases of satellite-to-satellite communications. Okay, well, let's have our satellite communicate with this other satellite to tell it that, get out of the way, we're coming. But when Starlink says we have this autonomous capability to detect and communicate and interfere and reduce interference between satellites that are in orbit, they don't have any way of doing that with other satellites. They just think they can do it with themselves. And a great example of that was a very close collision of an ESA satellite with Starlink last year, or maybe it was in 2019 at this point. But I think it's a great example of how we haven't figured out this communication mechanism yet between satellites, even if companies are saying we have it. And so we need to bring that to the fore. And the reality is that while we have these very hard engineering challenges, we haven't really fully thought about how those are additionally complicated by the cyber challenges on top of them. And so, for example, we talked about processing power a few seconds ago. Well, we also have the problem of we don't have a way of managing the communications between satellites. So let's say multiple satellites were communicating with one satellite at the same time. Are we going to have the likes of a DDoS attack on these systems? Absolutely, this is going to happen. And so we need a way of managing this. We also have the challenge of enabling, or because of the amount of server capacity or the computing infrastructure on these satellites, we're going to have the likes of data injection attacks that are possibly not real attacks, but there are accidents that can occur where maybe information is shared via an optical link in a way that wasn't planned. So maybe you have the incorrect configuration or formatting of that message, and maybe it will cause disruption to that satellite. Again, that receiver component, we haven't figured that out yet, and we really haven't thought about the security implications of this. And of course, you can do things to functionally encrypt your satellite communication with a laser, but at the same time, doesn't mean that you can't hurt the injection point of how those satellites are communicating in that receiver. We also have the reality of how data link are going to be disrupted by natural hazards, but also by jamming and communication and spoofing mechanisms. So we haven't seen the proof of concepts yet for how to disrupt laser comms and optical comms in orbit, but you can be sure that there are going to be mechanisms to jam laser comms, and that will cause critical vulnerabilities in these systems. And so I think one of the things that I wanted to kind of conclude with in my talk, because unfortunately the time here is not enough to go into a lot of technical details of how you would unfold these attacks, but the reality is we haven't really thought about how to solve these engineering challenges yet, but the security challenges are right along with it, and they're going to be compounding the engineering challenges. And so as we design these systems to communicate with each other, these constellations that are communicating with each other in space, we really need to kind of start considering not only what is the engineering behind actually functionally making that hard science happen, but the security pieces that come along with it. And by designing that in from scratch, we're going to save ourselves a lot of time and money and headaches in the future. So I think there's a whole bunch of opportunities to actually approach this challenge with. And so the first way we should think about this is we do have a relatively greenfield environment in terms of how we're actually planning the comms mechanisms between satellite infrastructure. And so it's possibly okay to try out some kind of crazy things that we wouldn't try on terrestrial infrastructure in terms of securing these assets. So is it about coming out with mechanisms for intercommunication linkages between satellites that require third-party metadata hashing to enable the validation of packages and packets? We don't have to rely on the way we've designed internet today. We can come up with new mechanisms for doing that. For example, there's a interesting proof of concept out of MIT called BlockSat, right? So how do we actually enable the blockchain to provide validation of communication mechanisms for space systems? It's a cool idea. Why don't we try that out? We don't have to rely on our legacy infrastructure. We also are increasingly seeing in the control system community and just the sale and opportunity of digital twins, and how digital twins can facilitate better control and testing and operations of commercial infrastructure for critical systems. And there's no reason to believe that we can't start designing digital twin systems for satellite links and be able to then do that parallelism and optimization accordingly to make sure that the communication systems are secure. And so these are just things that we need to start thinking about a bit harder. We haven't really addressed this question from a security standpoint yet because we still have engineering challenges to share. But I would encourage the community to kind of, let's get behind this now, because this is coming at us at a pace that we didn't expect. And I think we have a chance to make a change. So with that, I'll wrap up and offer to take any questions. I really hope that we can have a good discussion on this and get deep into some technical details as well if there's interest. So thanks again for the time.
Thank you, Greg. Thanks a lot. Very interesting topic because it's already quite overwhelming to grasp the full complexity of security for satellite systems, even single satellite systems. And now you're adding this extra layer of, guys, what's coming? It's satellite-to-satellite communications. So watch out, it's coming. But I think the approach is right. We need to have it in mind, and I absolutely concur with you. We need to talk about it to not face the same situation as we kind of facing today, launching satellites and then looking at security and say, what's up with the security? With what we discussed with Harrison before. Let's hear Patrick question. He had a good one.
Yeah, it's about your or the concept developed by MIT around the blockchain. What is your opinion? And do you have some more information about it?
Yeah, so I have to say first that I didn't develop that mechanism, so I can't speak to how I would design it differently because I haven't tested it out personally. But I think there's a lot of legs to engaging distributed ledger technology to enable these systems. And I think that there's some concepts that I'm throwing around right now with DARPA, which for project work, and I'm in the middle of writing a paper on it, which I'll share with the community as soon as I finish in a couple of weeks, hopefully, on how do we engage fully distributed communications in a way that is more advanced than we do here on Earth. So I think that there's a lot of opportunity there, and the first thing I would say is we shouldn't be afraid of using the word blockchain. Blockchain is a great distributed ledger technology. It has a lot of bad rap for a whole bunch of different reasons, but it's super useful, and it has in different use cases. And I think we need to embrace it in ways that aren't always embraced for regular commercial infrastructure because it has this weird tinged problem with it because of the nature of Bitcoin and illicit purchasing and things of that nature. But it's a really cool technology that we need to try and get behind and figure out the right use cases for space, because otherwise it would be a missed opportunity. And so, as I said, kind of stay tuned. There's some really exciting research that my lab's coming out with in the next couple of weeks probably that will talk about how do you engage certain types of distributed ledger mechanisms for communication in a robust way.
Excellent. Maybe if we put on the side the futuristic and potentially more groundbreaking ideas to secure satellite-to-satellite communications, what parts of the existing security mechanism could we reuse to secure satellite-to-satellite communications? I'm thinking about traditional cryptography, a bit what we talked about with Mark Manilis, or you mentioned also M2M, smart city. Can we reuse like existing building blocks also, or do we have to reinvent something from scratch?
Yeah, great question. I don't think I have a perfect answer to that. It's definitely going to require some testing to figure out what's useful. I would strongly encourage us not to just go down the traditional route because it's easy. If we could think of other more suited mechanisms to address these security challenges. So I'm not going to discount what we have today. I think obviously cryptography is phenomenal in the way we can use it when we use it appropriately. But it's also not the full stack solution by any means. I remember from my smart city days, they used to say, "Oh, we got security covered. It's encrypted," and all of us who were technically minded kind of rolled our eyes and said, "Well, you need a little bit more than that. Like it's a great start, but you can't just rely on that entirely." So I think that we can use some of this existing technology, but we do need to think a bit harder about the use cases and how we would engage it. One other thing I would add to this point is an area that I've been advocating for is figuring out how we can do more with taking existing health monitoring of satellites, because we are really good as a community with understanding health and reliability. I think Harrison even spoke about that today. And so since we're good about monitoring this, let's see if we can use those monitors from a security standpoint, repurpose the existing systems that we have on satellites to understand activity, and then begin to leverage this in ways that we haven't done so perfectly in the past. That's even an opportunity. So I think that we just haven't really prodded the bear enough, and we shouldn't just necessarily rely on existing solutions, but try and think a little bit broader.
Yep. One question from the chat, actually from Harrison, talking about him. He's asking you, what do you see as being the future of how space and terrestrial networks will merge? So really extending the terrestrial to the space network, combining it all together, forming like a 3D mesh.
Yeah, it's a really cool idea to think about. I think it's actually a lot closer than we believe, given the fact that Starlink is already they claim their own communication mechanism for their constellation, and they also obviously offer terrestrial internet. So, I think it's just a matter of time to hear what their plans are. But I do think, though, that there's going to have to be not an air gap necessarily, but there needs to be considerations for space systems that we don't have necessarily for internet systems, and make sure that these are not fully meshed kind of 3D environments. And the reason why is because we have safety reliability challenges in space that are maybe not as major impactful here on Earth. So, if let's say we have a disruption that results in a whole bunch of collisions in space, we're going to have a lot of problems when it comes to the increasing issue of space debris. And so it's kind of like having ASATs, right? Like that are just all over the place. Every satellite will make its own ASAT. So we don't want to fully merge these environments necessarily, because again, the surface area becomes crazy. But we also don't want a fully distributed infrastructure where there is no linkages. So again, don't have the answer to that, but it's something that we know is coming. We just need to kind of do it in a way that is not simple, because if we go the simple route, then we're going to end up with the same mess we have for terrestrial internet today.
Exactly. Great. Time is up. We'll have to move on. Thank you so much, Gregory.
Thank you for having me.
For the great talk. Thanks a lot. And
for the time.
Great to have you. Thank you for joining us.